Welcome back. I'm here on behalf of Forge College. In our last lesson, we took a quick detour to explore designing an AI-enhanced Solana development environment. Today, we are heading back to Ethereum. As you can see on our title card here, we are going to figure out exactly how to identify and prioritize bottlenecks. In plain terms, we need to determine exactly what to fix when a smart contract is running poorly. Think of the Ethereum Virtual Machine, or EVM, as a massive, high-speed restaurant kitchen. Your smart contract is the recipe, and those annotated execution traces you've been working on, they are the security camera footage watching the kitchen staff cook. Take a look at this footage of our chef running frantically. Notice how every single movement this chef makes costs actual money. In the EVM, we call that cost gas, and in our kitchen, gas bills add up incredibly fast. Reviewing the tapes, you notice a glaring problem. The chef is doing some exhausting, repetitive tasks. For example, they are walking across the entire kitchen 100 separate times just to grab individual peas out of the freezer. We know the execution flow is broken and wildly expensive. The challenge now is deciding which problem to fix first, without completely shutting down the restaurant to remodel. To start fixing our kitchen, we need to set up our workspace. We will place our raw security footage, our EVM traces, right next to a blank working document where we can record our observations. Here on this trace document, we are scanning for hot paths. A hot path is just a set of instructions that repeats over and over, draining gas each time, like our chef making those 100 trips to the freezer. Once we spot a hot path, we write down a potential fix. We will call this first idea Candidate 1. In the kitchen, this might mean moving the freezer closer to the stove. In code, this means we stop writing to the computer's permanent memory every few seconds, and instead wait until we have a whole pile of updates to send at once. Then we might spot a bigger issue, which becomes Candidate 2. This is like completely redesigning how your kitchen communicates with other buildings, moving away from those long chains where your contract has to wait for 3 other outside programs to answer before it can finish a single task. Your immediate goal in this step is to comb through your traces and extract at least 5 distinct bottleneck candidates like these. Every single one needs to be directly linked to specific lines in your trace evidence. Look at this 2x2 grid. We call this the prioritization matrix, and it is the tool that keeps developers from wasting days fixing the wrong things. The vertical axis measures impact, meaning how much gas we save. The horizontal axis measures effort, meaning how hard the code is to write and test. The top left quadrant is our high-impact, low-effort zone. Candidate 1, where we grouped our storage updates together, drops perfectly into this space. It is a quick code edit that yields massive gas savings. Over in the top right, we have high-impact, high-effort. Candidate 2, our big communication redesign, lands here. It will save a lot of gas eventually, but it requires extensive testing before we can trust it. Then there is the bottom right quadrant, low-impact, high-effort. This is a trap. You want to avoid spending weeks on complex coding acrobatics that ultimately save almost zero gas. Here is the flowchart mapping the entire execution process. As a final step, we take the top 3 candidates from our matrix and map them directly onto this floor plan, targeting exactly where the fixes will be applied. Mapping these out proves that your optimizations are highly targeted architectural changes, backed by hard evidence rather than random guesses. You do not have to fix every single line of code to make a smart contract dramatically more efficient. Watch how this chaotic kitchen drawing simplifies. The prioritization matrix focuses your energy exclusively on specific pressure points that actually move the needle. This process turns a confusing mountain of raw execution data into a confident, actionable plan of attack for your capstone project. With your top candidates successfully mapped, you are fully prepared to turn these concepts into real code upgrades and formal implementation strategies in the next step. This video was made by Forge College. To learn more about optimizing digital environments and other Web3 topics, visit us at forge.college.